there is one more thing I want to mention here with the partial differential equation, which is the partial differential equation as a mathematical object is a deterministic object. There is nothing random here. This partial differential equation has to hold for every t and every s. Okay, so this should hold for all t and s, as I said before, while t less or equal to t and s bigger than 0. And this is why we don't need randomness, because whatever s turns out to be, whatever the stock price in the future happens to be, this will always hold for all s, all t, and therefore the replication will work. Okay, and another thing, I'm not completely careful here with the notation. C is a c of ts. In this equation, c is really c of ts. Also, the partial derivatives of c with respect to t depends on t and s. This one, second derivative, depends on t and s. The first derivative depends on t and s. So there is t and s arguments everywhere here, just to make sure we understand that. All right, let's look at the Black-Scholes formula. So I told you they came up with this partial differential equation, and then for the call option, the function is s minus k positive part, or the maximum of s minus k and 0. That's what the function is. And the partial differential equation has a solution. Now, to find that solution, you have to be an expert in partial differential equations, or go to a textbook of partial differential equations and see how to construct a solution, which is probably what Black and Scholes did. Or I can just give you the solution, and then if you want, as an exercise, you can do calculus, you can find partial derivatives of that solution, check that it really is a solution. Okay? So I'm going to give you here a function, and in principle, you can take derivatives of that function that are needed in the Black-Scholes partial differential equation, and you could check that the left-hand side is equal to 0 when you compute all those derivatives and add them up. Okay, so I'm not going to teach you how to solve a partial differential equation. It's just I'm going to give you the solution they found, and if you read books on partial differential equations, maybe you could solve it on your own without me giving you the solution. And the solution looks like this. The function of t and st is composed of two parts: the stock price times some n of d1, which I have to tell you what it is. It's a probability, minus discounted strike price times n of d2, which is also some kind of probability, which I'll describe in a second. It's not very easy to give intuition why the solution looks like this at this point. When we do the second approach, which is not what the Black and Scholes did, and the second approach is going to be using martingale pricing, using expected value, then these probabilities will come up more naturally. But right now, it's not so easy to give intuition for them. The only thing I can say, well, if you look at the payoff here, it's a difference of s and k. Right? You basically have, at least when the option is in the money, it's s minus k. So yeah, here you have s adjusted by some probability minus discounted k adjusted by some probability. So somehow there are these two terms, the difference of s and k, but they are adjusted by some probabilities. How exactly these probabilities come up is going to be more clear when we do the other risk-neutral pricing approach. In terms of the exact definition of these n's, n is defined as a probability that the standard normal random variables, I'm using capital Z for the standard normal random variable, it's a probability that standard normal is less or equal to x. So it's what is called the standard normal cumulative distribution function, CDF, which can be written precisely mathematically as this integral. It's an integral under the Gaussian curve. So if you want a picture, let's try to do that. Right, so normal density, which is this function e to the minus y squared over 2 times a constant, looks, it's a bell curve, looks like this. So if your x is here, and let me just do that x more carefully. So if your x is here, and you look at the probability is this area here under the density. So it's this integral is area. So that area is n of x, right? That's your probability. Maybe if you are used to more mathematical notation, more typical mathematical notation, in probability books, this would more often be denoted by a capital phi of x. It's the same thing in option theory. Usually people use capital N for normal distribution, but in mathematics books you may see capital phi more often. Okay, that's what n is. N is the cumulative standard normal distribution function. And at which points is it evaluated? It's evaluated at points d1 and d2, and d1 and d2 have formulas which are written down here. And I don't want to go too much into this, except that everything is determined if you know volatility, sigma, time to maturity, capital T minus small t is the time left to maturity. Everywhere its time is in fact time to maturity. Strike price, current stock price, right? I'm looking at the current stock price, and then interest rate, and again volatility. Okay, so if you know those things, but you don't need mu, right? You don't need mu, but if you know those other parameters and, of the option and of the model, you can compute the Black-Scholes formula, and you can compute the value of the option, right? All right, so that's the famous Black and Scholes formula. They got the partial differential equation. They were able to solve it, and this is the solution. Let me just take a look and see how that looks in a graph. So for a call option, the payoff at the very end is this black line here, 0 below the strike price, and S minus K above the strike price. That's the payoff at maturity. The value, or the value at maturity, the value before maturity at some small t, so small t is fixed here, and I'm varying here the stock price. And the value before maturity is going to typically be looking like this, this blue line. So this is computed using the Black-Scholes formula for some particular parameters, including some particular time before maturity. So as you get closer to maturity, as capital T minus small t goes to 0, this blue line would get closer and closer to this payoff of the call option, piecewise linear payoff of the call option at maturity. It's going to be a smooth functions which will get closer and closer to this non-smooth piecewise linear function. Right? So this blue line gives you the values of the option price at that particular time, depending on where the stock price is currently. And different models would give you a different blue line. Okay? This is the Black-Scholes model, gives you this blue line. It's computed from the formula, but other models would give you the different values. And now for the put option, you can actually easily get the formula for the put option, because we have put-call parity, which is true theoretically in every model, in particular in the model of the Black-Scholes type. So we can compute put prices from the put-call parity, and for the put it looks like this. So the black line again is the payoff at maturity. Before maturity, it's going to be something like this. Okay. That's the put option. Fine. That's the famous Black-Scholes formula from 1973. Just to recap what we did, or what they did, they suggested a model with this geometric Brownian motion, exponential Brownian motion for the stock price. They derived a partial differential equation for the price from the logic that if you can replicate one asset by the other two assets, then you know what the value of that asset has to be. In this lecture, we replicated the put option price, call option price by trading in the bank and the stock. You get a differential equation, and then for some options, like call option, you can actually solve that differential equation, and that's the price of your option. All right, so that's it for this set of slides.